Hello everyone, welcome to my lecture series. So today we have already discussed about the basic theory, previous theory of sliding contact bearing. In this lecture, we will discuss some design considerations. Take a glance where we have discussed in last one. So we have discussed introduction, classification, then working, then different type of bearings, comparison. Now next one is a Petroff equation. So this equation is a very important point of as point of view of design of hydraulic journal bearing, because Petroff is the first scientist who designed or who con- uh, conduct some experiments with respect to the hydrodynamic journal bearing. The basic assumptions which he have used was as follows. The load is very light on the shaft that we call as a journal. The journal should be eccentric one so that the bearing can be easily withstand. Second one, the speed of rotation is high. So as the speed reduces, the hydrodynamic action get reduced. So to proper uh, for proper hydrodynamic action, the speed of journal should be high. Third one, the projected area of bearing is large. Yes, it is a very important task. If the projected area is very less, then the hydrodynamic action which we can generate by when the shaft journal get rotates, and because of the viscous fluid, this hydrodynamic action can be will occur, which will not be sufficient to separate the shaft, or you can say journal, and the bearing. And last one, the viscosity of lubricant should be high. If it is not, then it is very difficult to separate and to generate a high hydrodynamic action. So here few important uh, equations which we can found with the help of Petroffs equation. So according to the Newton's equation of viscosity, the tangential force acting on the journal due to the viscous drag is given by F is equal to mu into A into du by dy. So finally what we get, that F mu area, that is a 2 pi RL, and du by dy, that is du u by c, that is 2 pi r ns divided by c, where mu is the absolute viscosity in this equation, but normally we are denoted with the help of PSG. It is denoted by z dash. In this equation, we will discuss for this equation only. Then further, in a further design, we will discuss uh, how we can design based on PSG. So here, small r the radius of journal, capital R the radius of bearing, L is the length of bearing, C is the radial clearance, B small p is the bearing pressure, and U is the surface velocity of journal, which is meter per second, area A, and F is the frictional coefficient of friction. So next one, the frictional torque acting on journal due to the drag, that is F into R. So final equation, 4 pi square R cube mu L ns divided by C. By considering the friction for calculation, the frictional torque acting on journal Tf is equal to F into W into R, that is 2FPL square. When we compare equation number 1 and 2, where in one equation we haven't considered friction, and second equation we have considered friction. So based on this, how we can find out the Petroffs equation for calculating of coefficient of friction, that is 2 pi square. When we equating this equation, we get final Petroffs equation, that is 2 pi square mu ns divided by p into r by c. Okay, and this is very important equation when we calculating the, when we have a different parameters and we need to calculate the coefficient of friction. At that time we are using this equation. Now one more thing is that there are two-dimensional parameters, that is a ratio of mu ns divided by p and r by c. The Petroff equation, or we can say analysis, is applicable when the journal is a concentric to the bearing. This is possible when the speed of rotation of the journal is very high, as applied load is very light, or you can say moderate. The Petroff analysis gives, or this equation gives a responsible for fair estimation of coefficient of friction, as we found that the final equation which is for coefficient of friction for the value of eccentricity ratio, that is small e, which will be in the range of 0.0 to 0.5, and based on the data we can finally develop a hydrodynamic theory remaining, which is based on the Reynolds equation, as we using Newton's viscosity equation over here. So for further calculation they have used Reynolds equation. Now next one is a nomenclature of hydrodynamic journal bearing. So we should know what are the basic parameters which we have to use for design calculation purpose. So first one is a radial clearance, which is nothing but a difference between radii of bearing and journal, which is denoted by c. Then second one is eccentricity. It is the distance between the center of bearing and the journal in an operating condition. So due to the hydrodynamic action, if we consider at the initial stage, or if you remember the first lecture in this, that we was seen that at rest condition the journal and bearing are having a metal to metal contact. So at that time the difference which is obtained in between the axis, or we can say vertical horizontal axis, that is we normally say as a eccentricity. Minimum oil film thickness. It is the oil film thickness along the line joining the center of journal and bearing. So it is very important. If the minimum oil film thickness, based on the minimum oil film thickness, there are various type of lubrication patterns are there. Now next one, fourth one, eccentricity ratio. The eccentricity ratio is the essence, it is the ratio of eccentricity to the radial clearance. So based on this we can find out any one of them. If we have the value of ratio, we can find out the other one. Next one, minimum oil film thickness ratio. It is also very important, because based on this we need to find out the calculations. Okay, this will better we can understand when we solve the numericals. You just at this time you just understood what are the different nomenclatures or parameters which we can use for design of hydraulic bearing. So these are the dimensionless parameters. In examination for 5 marks theory, they may be asked regarding to the write down the different type of dimensionless parameters. So why it is necessary because we need to calculate sommerfeld number, then length ratio, length to diameter ratio, that is L by D, minimum oil film thickness variables, eccentricity ratio, then coefficient of friction, that is variable, flow ratio, maximum film pressure ratio, position of maximum film pressure or maximum film pressure angle, zero pressure angle, position of minimum film thickness or minimum film thickness angle, or temperature rise variable. So these are the basic dimensional parameter which we must have to use while design. Okay, how we can use, how we need to use, that will be discussed while designing. So, which parameter should consider for hydrodynamic journal bearing design? There are two type of variables are there. First one is a design variable and second one is a performance variable. When we consider a design variable, the variables which or those whose values are either given or under the control of designer. So these variables or these parameters can be designed or can be controlled by the designer. So which are the first journal speed, second viscosity, third one is a unit bearing pressure or you can say load on unit projected area. Third one or last one, that is a fourth one, that is a bearing dimensions. You can say uh, radius, clearance, then length, and the arc of bearing, that is the angle. Okay, so out of these four variables, the designer usually has to control over the speed, because we cannot control the speed because it is specified by the application itself. So based on the application, we can consider or we can adjust the speed. The remaining variables can may be controlled by the designer. Okay, next one. When the four variables are defined or selected, the designer bearing is completed. So for complete design, basically these parameters should be known. इफ इट इज प्रॉपरली हम लोग इसको अगर कैलकुलेट करते हैं तो हमारा बेसिक डिजाइन जो रहता है विद रिस्पेक्ट टू द हाइड्रोडायनामिक बेयरिंग वो कंप्लीट हो जाता है, बट वी नीड टू एनालाइज देम. सो दैट्स व्हाई वी goes to the second type of variable, that is a performance variable. The performance variable, those tell us how well the bearing is performing, and these parameters we cannot control by designer. So this variable except directly by changing one or more type of design variables. In order to ensure the satisfactory performance of the bearing, the designer must impose the certain limit to the values of performance variable. These limits are based on the characteristics of bearing, material, and lubricants. If we cannot provide the limitations, then it can be performed variantly, and it should not be happen. So while designing the hydrodynamic bearing, which is nothing but satisfy the limitation of the performance variable, and then decide the values of design variable such that the performance variable do not exceed the defined limit. So this is a simple definition, or you can say simple definition of design of hydrodynamic journal bearing. Now this is the basic procedure of hydrodynamic journal bearing design. So initially what we needed, the input needed are length by diameter ratio, then bearing material, general speed, or we can say initially we need bearing pressure. Okay, so these are the basic inputs which we needed. What next we can calculate? Based on this, we need to calculate the, if we have a load and area, we can calculate the bearing pressure. After the calculating the bearing pressure, you can find out the radial clearance by using a specific application through the PSG. After the calculating the radial clearance, we need to calculate C0 twice C0 by C ratio, and based on this we need to calculate a sommerfeld number. Okay, and after the sommerfeld number, or you can using the minimum oil film thickness ratio, and with the reference of these dimensional parameters, you can find out the other parameters, that is sommerfeld number, then Q by Q ratio, then Q by RC NSL ratio. Okay, so these ratio we can find out. So based on these equations 1, 2, 3, 4, 5, we can find out the 5 parameters, dimensional parameters, that is the eccentricity, then absolute viscosity, coefficient of friction, the total flow rate of lubricant, and the side leakage of lubricant. Now next, about the temperature gradients, we need to assume initial temperature. If we don't have, we need to assume. Then take an average value of specific heat density based on the condition of the for the proper condition, proper based on the proper value of absolute viscosity. Finally, we can calculate the total temperature rise as initial temperature and the final temperature. So if the temperature rise in a proper limit, then and then only we can accept the design. Otherwise, we need to redesign, or we have to change our design variables so that the performance variable can be within a limit. Okay, so this one is a design. So we will design a simple okay, as we have already discussed about the design procedure, let's start with the design of full journal bearing. Okay, so consider a 360 or a full journal bearing, hydrodynamic bearing, supported a load of 20 kilonewton when operating at 1000 rpm for a steam turbine. So here as the application is given, that is a steam turbine. If the allowable bearing pressure is 1.6 Newton per mm square, we need to determine first diameter and the length of the bearing, second the clearance ratio, third one is the minimum oil film thickness, fourth one is the viscosity of oil, fifth one is the coefficient of friction, sixth one frictional power loss, seventh operating temperature of oil. So what we have given, so first of all we need to note down what are the given parameters are given. First, load, that is W, is equal to 20 into 10 raised to 3 Newton. Then speed, journal speed. So here in our design, referring the PSG, we need to use a journal speed in revolution per second rather than revolution per minute. So we have divided the value of RPM, that is 1000 RPM divided by 60. What we get? 16.667 RPS. Now next one, to calculation of the bearing diameter and the length. As we know that the application is a steam turbine. So if it is application given, we need to find out what should be the range of L by D ratio. So for that we need to refer PSG. Okay, so you can use the PSG start with the 7.28 where properties of lubrication are given based on the application. Then materials for journal bearing, which is also classified with the character, limitation and application. Then the design parameters. Now at this point we have to decide. Here they have provided the values of Here in this table they have provided application, type of bearing, L by D ratio, bearing pressure values or range, then Z, the absolute viscosity in centipoise, and the Zn by P ratio. So here what we need to calculate, first we had to find out the proper application. Our application is steam turbine. So this application I have chosen. Now L by D ratio. So here the L by D ratio which is given is in between the range of 1.0 to 2.0. आप L by D ratio 1 भी use कर सकते हो, 2 भी use कर सकते हो. So here in our design we have selected N by D ratio is 1. L by D ratio is equal to 1. Now to find out the actual value, we have a bearing pressure which is given in a problem, that is 1.6 Newton per mm square. So bearing pressure is equal to load divided by projector area. Load which is denoted by W, projector area is nothing but L into D. As the L by D ratio is 1, then L is equal to D, that is a D into D, D square. So putting all the values, what we get, D is equal to 111.88, which we can directly modify to the 112 mm. So length and the diameter of the bearing are 112 mm. As we are using L by D ratio is equal to 1. Now next step, we need to calculate the diametric clearance, or you can say clearance ratio. I said rather than this I use diametrical clearance. How we can use, just go to the PSG. So in PSG page number 7.32, there are various values based on the diameter are given. So our diameter is in between 90 and 140. So in this application I have chosen basically the electric, as we have using a turbine or steam steam turbine. So I'm considering the application point of view. Now here I am considering the electric motor and generator, which we are always working with the similar speed, and based on that our values are ranging in between 90s and 140, as the value of D is 112. So here I am considering the direct value. The maximum value of diametric clearance for 90 mm diameter is 100. So I'm directly considering the value of C is equal to 100 micron. You can choose in the range of 100 to 150, but if you consider value, if you increase the value more, so we need to increase the diametrical pressure. Okay, so here let's go to the design again. Okay, next step, calculate the absolute viscosity of oil. Here again we need to select from PSG, referring PSG page number 7.31. So for similarly, as we previously selected for steam turbine application, the value or range is given over there. So the value of Z, or you can say the value of Z over here, I am showing over here, it is ranging between 2 to 16. 2 to 16. We have selected 10 Okay, so the value of absolute viscosity, that is at 10 centipoise. So 10 centipoise by using equation for to calculate the absolute viscosity, which is given in PSG. So from this page 7.31, we have calculated the value of absolute viscosity. Now we need to calculate actual value of absolute viscosity in proper dimensions. Okay. So Z dash is equal to Z divided by 9.81 into 10 raised to 7. So similarly, whatever the value we get, we can convert into the Newton second per mm square. Okay. So here in numerical, we have done that. We have directly convert the values and given to the design. Okay, so all the values which we have considered, which is in a Newton. Okay, so here the z dash, z is equal to 10. So putting in the equation, what we get, z dash is equal to 1.019 into 10 raised to minus 7 Newton second per mm square. Next step, the calculation of sommerfeld number. Yes, it is a very important, as we previously discussed. The sommerfeld number having two-dimensional parameters. Based on this, designer variables are over here. So while selecting the other parameters, that is a performance parameter, which we can handle or which we can limit from here only. So अगर हम लोग समरफील्ड नंबर प्रॉपरली सेलेक्ट नहीं करते तो हमारा बेरिंग डिजाइन परफॉर्मेंस लिमिट के अंदर नहीं रहेगा. ओके, सो to control the performance parameters, we have to select a proper value of sommerfeld number. Referring PSG, we can calculate the sommerfeld number. PSG page number 7.34. In this segment, you can find out the equation for sommerfeld number. S is equal to Z dash N dash divided by P D by C bracket square, where Z dash is absolute viscosity, N dash the general speed in RPS, P is the bearing pressure, D is the diameter, general diameter, C is the diametric clearance. So we have put it, we have all the values which we have calculated and also selected from proper PSG. So putting all the values, what we get, the value of S is equal to 1.33. Now, based on the L by D ratio and the sommerfeld number, how we can find out these dimensionless parameters? So we can select, go to the PSG, open the PSG page number 7.37, 7.36, sorry, 7.36, where the dimensional performance parameter for full Jernung bearing with side flow are given. So here in this area, they have provided L by D ratio. Then this column is for dimensional parameters. For each parameter, they have provided a proper values based on the L by D ratio. So what we have L by D ratio, that is a 1. Then the value of sommerfeld number 1.33, which is calculated. Okay, now how we can find out the other? Now we have to consider this one is a 1. If it is a half, then we have to consider this one. If it is 0.25, then consider this one. If it is infinity, that is a more than 1. You can also refer this segment. Now, as the diameter d by L by D ratio is 1, we need to refer this area. Okay, so I just highlight this one. Now, as per the Sommerfeld number, that is a 1.33, we need to refer this row. Okay, so the value of 2h by c, the value of 2h by c is 0.9. The value of phi is 79.5. The ratio of mu into d by c is 26.4. Then the ratio of 4q divided by dc and dash l, which is equal to 3.37. Then ratio of qs by q is equal to 0.15. Ratio of rho c dash delta T0 divided by P is equal to 106, and the last ratio is P divided by P max is equal to 0.54. So these are the dimensionless parameters which we can easily found based on the only two values. What we need two values, that is Sommerfeld number and the L by D ratio. अगर हमारे पास ये दो values है तो हम लोग कोई भी dimensionless parameter find out कर सकते हैं. अगर एग्जाम में और प्रॉब्लम में आपको अगर मिनिमम ऑयल फिल्म थिकनेस एंड डायमेट्रिक क्लियरेंस दिया रहेगा, then you can first of all calculate the 2H0 by 2HO divided by C and fix the L by D ratio. If it is fixed by 1.5, then you can refer this column. Okay, so whatever the value you get, for example, if you got a value of 0.8, then consider this whole row. Okay, so that you can directly find out the other parameter values. So if you consider 2HO divided by C, L by D ratio is 0.5. The Sommerfeld value, now the Sommerfeld value is 2.03. Okay, similarly you can find out for other. Hope you can understood. Okay, so note down these dimensional parameters and which we needed for further calculation. So I have noted down all the parameters. Now next one, to find out the minimum film thickness. Okay, so it's very easy task to calculate the other parameters or performance parameter also. So directly we can consider twice H0 by C is equal to 0.9. So H0 is nothing but a minimum oil film thickness. So putting the value of C, what we get, we can directly find out the value of H0, that is 0.045 mm. Next one, coefficient of friction. So next values we have, next dimensionless parameter we have considered mu into d by dc, sorry, mu into d by c, that is a coefficient of friction into general diameter divided by diametric clearance. So it is, this equation is equal to 26.4. Putting the value of C and D, what we get, mu is equal to 0.023. Next one, the frictional power loss. Okay, so remaining parameters we can use for what parameter we need to calculate. Okay, now next one, as per the problem, we need to calculate the frictional losses or power loss. PF is equal to 2 pi ns into mu into W into R. That is a radius. Putting all the values, what we get, the frictional power loss is equal to 2.69 kilowatt. The equation is very simple, which we have already used in our basic designs. Next one, next step, we need to calculate the flow rate of lubrication of the oil, that is a Q. Again, we are referring the dimensionless parameter, that is a 4Q divided by DC and dash L is equal to 3.37. So we know the value of diameter of journal, then diametric clearance, then speed journal of speed in RPS, and the length. So putting all the values, what we get, Q is equal to 17,614.21 mm cube per second. Next step, we need to calculate the operating temperature of the oil. So here, to calculate the variation in the temperature, we had to compare the heat generated and heat dissipated. So heat generated we can find out with the help of equation. We have two methods based on first method. By empirical relation we can directly find out the frictional power loss, that is a rho q cp delta t into bracket 1 minus 1 half qs by q divided by 10 raised to 8. By referring PSG page number 7.36, what we get? We get the direct density of oil, that is a 830 kg per meter cube, and the specific heat of oil, that is a 1.71 kilojoule kg degree per second. So putting all the values, what we get, the temperature change, that is a delta T, is equal to 11.63 degrees centigrade. As we considering the initial temperature of 30 degree, that is operating temperature, the variation should be the half of delta T. So T1 plus half of delta T, that is equal to total variation, or you can say the operating temperature of the oil is 35.815 degrees centigrade. Now similar values we can find out by using a dimensional parameter. By referring equation rho c dash delta T0 divided by P is equal to 106, where rho c dash is equal to 14.2 Newton per mm square degree centigrade. Okay, and we know the P, the value of P is a bearing pressure, that is a 1.6. Okay, so putting all the values, what we get, the delta T is equal to 11.94, and here with the help of parametric equation you get the value of 11.63. Okay, any method you can choose, you can find a proper value. Okay, so delta T divided by 2, what do we get, the operating temperature is equal to 35.97 degrees centigrade. So here is the 35.815 and here is a 35.97, which is nearly equal. Okay, so you can use dimensional parameters, dimensionless parameters and find out the operating variables properly. Okay, so rather than using this step, you can directly go to this one. So that's also we can these are two steps we are using for validating purpose. So that's why I go with step 1 as well as step 2. Okay, so the final output which was 35.8 and 35.9, which is approximately near equal. Okay, so in this manner or in this process you can directly easily design any type of sliding contact bearing. I hope you have understood the design procedure, how we can refer the PSG and how we can use the dimensionless parameters for calculating the performance variable of sliding contact bearing. Okay, so thank you very much for joining this lecture. In next lecture we will discuss another another type of numerical, which is for full journal pairing, as well as we discuss how we can use if the value of sommerfeld number which is in between two given number. Okay, so we will discuss in the next lecture. Thank you very much.